Well, in section 3.4, we're going to talk about finding the real zeros of a polynomial. Now, real zeros mean they actually can occur. They will not have imaginary solutions or anything like that. And we're going to go through a problem or two and basically kind of give you everything that you can have in order to help you do that. Do you use everything all at one time? Not necessarily. It's all up to you. But there are some things that will help you along your path to finding the zeros. The first thing that we're going to find is we're going to use what we call the rational zeros theorem. Now, what the rational zeros theorem is basically coming up with and generating a list of possible solutions for you to find. Right now, if I gave you a polynomial and said find the zeros, I'm not specifying everything in the world imaginable for number-wise would be at fair game. What this is going to do is eliminate it down to a list. Now, that list could be substantially big or small depending on the numbers, but the rational zeros theorem will help us get it down to a list. Now, the formula says P divided by Q. And what P and Q are, P is all the factors of the constant divided by Q, which is all the factors of the lead coefficient. There's that lead coefficient again coming into play, like it did in finding end behavior. So it's still P and Q, it's just that's what we're referring to. So when they ask you to come up with the list, they're just asking you to find all the different possibilities. And so if I gave you a polynomial that said P of x equals, let's go 3x to the third plus 2x squared minus 7x plus 6. First thing I would do is I would list all the factors of the constant, which are 1, 2, 3, and 6. And just to kind of give you a little bit of a background, the reason why I put plus or minus 6, regardless of whatever the number is, you should always use plus or minus, and the reason for that is because if I were to take 1 times 6, I would get 6, but also if I took negative 1 times negative 6, I would still get 6. It's just a shorter way of writing down all the numbers instead of writing out every positive and negative number that we have. Then the next thing I would do is write plus or minus 1, plus or minus 3. Those are the factors that multiply together to give you the lead coefficient. Now what I'm going to do is I'm going to take every single one of the top ones divided by every single one of the bottom ones. So 1 divided by 1 is 1. 1 divided by 3 is 1/3. 2 divided by 1 is 2. 2 divided by 3 is 2/3. 3 divided by 1 is 3. 3 divided by 3 is 1. I already have it. There's no need to write it again. Plus or minus 6, because 6 divided by 1. And then 6 divided by 3 is 2. I don't need to write it. Here's my list of possibles. Now, I went from every number in the world down to that list. It's still a decent-sized list, but it's a lot lower than what it was, or what it could have been. That's how the rational zeros theorem works. This is the step I would suggest that you start out by doing. When they ask you to find the zeros, whether it's real zeros or the zeros, always start with the rational zeros theorem. Get a list of possibles. That's the first thing we should do. Then after that, then you start dividing. And we divide by using synthetic division. Do not long divide these. It would take too much time and paper. So when you're doing this, use synthetic division. Make sure you use pencil, because if you get something wrong or it doesn't work, then we just erase and we start over. If you're using pen, you're going to waste a lot of paper. So be careful with that. With that concept. But that's the first thing that you should do. Second thing that we can do in order to start. Now, again, I'm going to give you all the tools first, and then we'll go through a problem. Is using what they call Descartes' rule of signs. Now, the reason why it's called Descartes' rule of signs is because it was named after a French mathematician by the name of René Descartes, who did a lot of things in math, and one of them was the Cartesian coordinate system, or the coordinate plane that we graph on, but also this rule of signs. And the way it works is, is it has the number of positive real zeros is either equal to, the number of sign variations, and I'll walk you through one here in just a second, in your polynomial, or is less than by an even whole number. Now, what this fancy thing says is basically, I'm going to look at the polynomial and I'm going to count how many sign variations does it have. How many times does it go from positive to negative? All the way across. Whatever that number is, that's how many positive real zeros we can have. And then we decrease it by 2, and that's how many it could also be. And the reason why we decrease it by 2 is because when we find imaginaries in section 5, those always come in pairs. So if we take those pairs out, we would only have those positive ones left, or negative ones. So for the number of positive real zeros, it's either equal to the number of sign variations or is less than that by an even whole number, which basically means decrease it by 2 every time. The second half of this says the number of negative real zeros is either equal to the number of variations in sign in P of negative x. And what that means is we're going to put negative x in and simplify it and then count how many sign variations there is. Or is less than that by an even whole number. So it works very similar to what we just talked about with the positive ones, but that's Descartes' rule of signs. That's how it's listed anyway. I'm going to do the exact same problem and then just show you what I mean by the number of sign variations. Or maybe I'll give you a different one here and find one that I know would be a really good one to look at. So if I have P of x equals 3x to the 6th plus 4x to the 5th plus 3x to the 3rd minus x minus 3. What I'm going to do here is I'm going to count how many sign changes do I have according to the original. So from here to here, did the sign change? No. From here to here, did the sign change? No. Did the sign change here? Yes. Did the sign change from there to there? No. So this went from positive to positive, which is no. Positive to positive, which is no. Positive to negative, yes. Negative to negative, which would be a no. There is one positive real solution, or real zero, in this particular problem, according to Descartes' rule of signs. Now, what that means for us is, do you remember that list that we created using the rational zeros theorem? Now, if we find one positive real solution that works, that's awesome, because now I can get rid of all the other positives. That's what this thing will do, is help you eliminate some of the possibilities out of your list. Now, if I throw in negative x into the problem, I end up with 3x to the 6th minus 4x to the 5th minus 3x to the 3rd plus x minus 3. Let's count sign changes. Positive to negative, 1. Negative, nope. Negative to positive, 2. Negative to or positive to negative, 3. I have, in this problem, 3 negative real solutions. Or zeros, I mean. Excuse me, we should call them zeros in this. Okay? So if that was the case for that one, then right now I have a grand total of 4 different possibilities when the final answer tells me I should have 6, and that means I probably have some imaginaries with this one. We're not actually going to find these, we're just going to count how many. What Descartes' rule of signs could do, again, is take that list that we had generated using the rational zeros theorem and reduce our possibilities. That's all the Descartes' rule of signs does. It just reduces the possibilities. Then the next thing that they do for us is they talk about an upper and lower bounds. And this occurs when you are dividing using synthetic division. And if you notice a couple things, I'm not saying I want you to go out and find the upper and lower bounds. I would say, use it to help you eliminate your list or get your list lower. That's all that this really is it occurs, both of them that is, in synthetic division. And that's the step that we're going to do after that. On the first one, it's an upper if all answers row is positive, including remainder. Okay, so what that means is if I synthetic divide it and I got no negatives across the board, everything's a positive, including the remainder, which means it's not 0, then it's an upper bound. It's a lower bound if the answer row alternates signs. So that means don't try anything lower than that. So if you put in like a -3, for instance, and all the signs alternated from positive, negative, all the way through the whole way, then if you had -6, -9, -10, 12, whatever, don't put them in. Those are gone. Take them out of your list. So it's a way to get your list down. You want to try to get your list down to as minimal as possible. And there's the only other things that's also important to know is to remember the quadratic formula. The quadratic formula is something, again, that you guys saw in chapter 1, but on a lot of these, when you get to synthetic dividing, you get to be doing synthetic dividing so much, and if you can't find the answer right away, you're going to get sick of synthetic dividing. And it's one of those things where, hey, once I get it down to that quadratic type, or I get it down to something squared, I'm just going to put it in the quadratic formula and move on. I don't want to have to worry about trying to find any more. So what the directions will say, it'll say find all the real zeros. Sometimes it'll say write it in factored form. Sometimes it'll say use the quadratic formula if necessary. Sometimes it'll just say find all rational zeros. And then irrational zeros, or find all the real zeros of the polynomial. And then wherever appropriate, use whatever you want, whether it's the rational zeros theorem, upper and lower bounds, Descartes' rule of signs, quadratic formula, other factoring, whatever you need to do. So in a problem that I'm going to do with you guys is I'm going to take something like this. I'm going to go P of x is equal to x to the 5th minus 7x to the 4th. That looks like a 9. Plus 9x squared, or cubed, plus 23x squared, minus 50x, plus 24. So the first thing is that you want to do when you have a problem set up like this is let's get the list of possible solutions. So the first thing I want to do is have you guys come up with what times what gives you the constant. 1 and 24 multiply together to give me 24. 2 and 12 multiply together to give you 24. 3 and 8 multiply together to give you 24. 4 and 6 multiply together to give you 24. And nothing in the middle of between 4 and 6. In the front I have a 1, so that would be where I am multiplying everything by 1. Where I'm dividing everything by 1, so I would not need to multiply or do anything like that. So from here, I'm going to just choose one of the numbers. It's like rolling the dice, where you don't know what's going to come out. You just roll it and hope for the best. What you're looking for is you're looking for the remainder to be 0. That's what you're looking for. So let's say, for instance, I throw in the number 3, and I'm going to put it in a backwards L, and I'm going to use synthetic division. I'm going to put all my numbers going across. And I'm going to divide. 1 times 3 is 3, minus 4, negative 12, minus 3, negative 9, 23 minus 9 is 14, times 3, 42, right? Negative 24, and 0. So I got lucky. I found one right away, where I didn't know it was going to happen, but I found one because this number right here is 0. So that is one of my answers. Now the next thing you should do is try it one more time. Remember in the last section we talked about multiplicity. That means that if it shows up, it could show up more than once. So if I multiply that again, I could end up having the same thing twice, which in this case, that would be kind of nice where if I had the same number twice, we'd have another one done. Unfortunately, when I multiplied that through, it did not work. This is where the pencil and eraser comes into play. I just go back and erase it, and I start over. And I pick a different number. So what's a number different than 3? Let's try 1, just because. Again, we're rolling the dice and we're trying to figure out what works. We don't know what works. Okay, we're trying it out. Oh, look at us go. We found another one. Again, I'm going to try 1 more time. And notice what I'm doing. I'm not putting it back to the original. I'm putting it to the new line. And that's the reason why I'm doing that is I'm trying to get it reduced down so that way I don't have so much to deal with. I only have a couple things. 1 is negative 2. Negative 2 is negative 8. Negative 8 is 0. And look at there. No, the number 1 worked again. Now what's happening is I started with something to the 5th power. I have found 3 answers, which means this is now x squared minus 2x minus 8, which then from here I know that that factors into this, and I can set each group equal to 0, and I end up with all 5 answers. So one thing I wanted to point out with this is that I used the rational zeros theorem. I did not have to use the upper and lower bounds theorem because it didn't show up. I did not use Descartes' rule of signs just because I don't usually like to do it. But what I would have done if I was going to use Descartes' rule of signs, I would have counted 1 sign change, 2 sign change, 3 sign change, 4 sign change, which means there should be 4 positive, 2 positive, or 0 positives. In this particular problem, 1, 2, 3, 4, we got 4 positives, which means then 1 negative should be left over. So if that's the scenario, then that's how many answers I should have got. If this was the scenario, there should have been 3 negatives to make 5 total, or 5 negatives to get that total. Or if you throw the imaginaries in there, which we will in the next section, then we could have a whole nother outcome. But this is what section 4 is all about. They just give you a few different problems with it, but realistically, that's the type of question that you should be asked, is find the zeros or find the rational zeros. Now let me give you another one that has a number in the front, so that way we have a little bit different style list here. to the fourth plus 3x to the third minus 4x squared minus 3x plus 2. So if what times what gives me 2 is 1 and 2. And what times what gives me 2 in the front is also 1 and 2. So this 2 is for the top, and this 2 is for the bottom. And if I multiply or divide everything out, I have 1 divided by 1 is 1, 1 divided by 2 is 1/2. 2 divided by 2 is 2, and 2 divided by 2 is 1, and then 2 divided by 1 is 2. So there's my list. Now as far as coming up with the possibilities, I'm just going to try the number 1 and see what happens. Maybe it works, maybe it doesn't. 2, 3, -4, -3, +2. Drop the 2. 1 times 2 is 2. 3 plus 2 is 5. 1 times 5 is 5. 1, 1, -2, -2, and 0. We hit a home run. If I throw a 1 in there, 7. 7 is 8. 8 and it's not going to work. So therefore we just take our eraser and we erase out the bad stuff. And we try a different one. I'm going to try a -1 just because I don't want to change that number. But again, me picking what number doesn't matter. It's one of those things where if it works, it works. And if it doesn't, oh well, you throw it away and you go from there. So right now I found 2, which means I went from a 4, I've got it down to 2. So this is really 2x squared plus 3x minus 2. Hey, I'm going to try to factor a quadratic formula. If it factors, that goes faster. If it doesn't factor, this is where I would use the quadratic formula, which in this particular context, it does factor. And if I set each group equal to 0, I'd have x equals 1/2 and x equals -2, and I would end up having all 4 answers. So as far as section 4 goes, that's what they're going to ask you to do with that list of possible solutions, or that list of different ways of solving it. That's what they're asking you to do. You can use them if you want or not. It's totally up to you. So anyway, that was section 4.